Over the last few years, nitrosamines have completely changed how we think about pharmaceutical quality. What makes this topic particularly challenging is that the root cause is often invisible. In this presentation, we're going to take a deep technical investigation into excipient variability and how something we've traditionally considered inactive can directly impact nitrosamine formation. This is not just a regulatory story, it's a chemistry story, a formulation story, and most importantly, a prevention story. This story starts with an unexpected crisis. Product that had been on the market for years, sometimes decades, suddenly began failing for nitrosamines. There were no formulation changes, no process deviations, and the API? Completely stable and unchanged. Naturally, the initial investigations focused on the API, but as data accumulated, something didn't add up. The real culprit turned out to be excipient variability, something that had always been there but never fully questioned. For years, these products showed consistent quality and clean stability data. Then suddenly, during routine stability testing, nitrosamines appeared. At first, the assumption was simple. Something must have changed in the API. But analytical and supplier data showed the API was stable and unchanged. What had changed was far more subtle. The excipient was variable, chemically reactive. And under the right conditions, it became the trigger for nitrosamine formation. This forced the industry to rethink a long-standing assumption, that excipients are chemically passive. To understand why excipients matter, we need a quick technical refresh on nitrosamines. Nitrosamines are potent genotoxic impurities, which means even extremely low levels are unacceptable. Chemically, they form when secondary or tertiary amines react with nitrosating agents, most commonly nitrites. Importantly, this reaction does not require extreme conditions. It can occur under mild heat, in the presence of moisture, and during long-term storage. This means risk can come from trace levels that were never considered critical in traditional excipient testing. We often describe excipients as inactive, but chemically, that's a dangerous oversimplification. Excipients come from natural sources, fermentation processes, petrochemicals, and complex multi-step syntheses. Each of these steps introduces opportunities for residual impurities, degradation products, or variability. Even excipients that look identical on paper can be chemically very different. The key insight here is critical. Excipient variability is not a quality failure. It is a predictable chemical reality. Excipient variability doesn't happen randomly. It comes from very specific sources. Different raw materials can introduce amines that later participate in nitrosamine formation. Manufacturing process changes, such as switching solvents or catalysts, can introduce nitrites or nitrates. Purification and drying steps matter too. High temperatures can concentrate impurities, while poor drying leaves residual moisture. And finally, storage and transportation conditions, especially humidity, can enable slow chemical reactions over time. All of this variability can exist even when excipients meet pharmacopoeial requirements. Some of the most commonly used excipients carry hidden nitrosamine risks. Microcrystalline cellulose has been shown to contain trace nitrites. Starches can pick up nitrite contamination during processing. Lactose may contain amine residues from processing aids. Povidone can introduce nitrites during its synthesis. Individually, these levels seem insignificant. But when combined with an API containing amines, and given enough time and moisture, they create ideal conditions for nitrosamine formation. Let's walk through a realistic formation pathway. You start with an API that contains a secondary amine, perfectly legal and well understood. You add an excipient that contains trace nitrite, well below pharmacopoeial limits. Residual moisture is present, as it is in virtually all pharmaceutical products. The product is sealed and stored. Nothing happens immediately, but over months or even years, a slow reaction occurs. By the time stability testing is performed, nitrosamines have already formed, quietly and gradually. This brings us to a hard truth. Compendial tests were never designed to control nitrosamine precursors at ultra-trace levels. Pharmacopoeial limits allow a degree of variability that can be problematic when APIs contain amines. So, an excipient can fully meet USP, EP, or IP requirements and still pose a nitrosamine risk in your formulation. This is not a regulatory failure. It's a reminder that risk-based thinking must go beyond simple compliance. Effective prevention starts with a systematic risk assessment. First, characterize the API. Identify amine functionality and reactivity. Next, evaluate excipients for nitrite content and batch-to-batch variability. Then, map potential interaction pathways between API and excipients. Finally, assess worst-case scenarios using stress conditions. The key shift in thinking is this: excipients must be treated as active participants in formulation chemistry, not passive fillers. Think worst case, not typical case. Managing nitrosamine risk requires layered control strategies. It starts with deep supplier qualification, understanding the process, not just reviewing the certificate of analysis. Internal excipient limits may need to be tighter than pharmacopoeial requirements. Formulation controls like antioxidants, pH adjustment, and moisture reduction play a critical role. And packaging choices, especially moisture barriers, can significantly reduce long-term risk. The takeaway is clear. Excipients deserve the same scientific respect as APIs. In today's regulatory and quality landscape, this shift in mindset is no longer optional. It's essential.